So anyway, and I will post last time's video up soon. The main thing about that is that when it comes to, right, we did 2D rigid rotor, 3D rigid rotor, and then I filled in some of those blanks with like particle in a three-dimensional sphere. So it's like particle in a box, except it's three-dimensional and the thing is round. So I told you a little bit about that. The main thing about all of that business is I just want you to get as used to humanly possible about how the separation business funnels the thing we care about, eigenvalue of energy, that gets funneled down into a sub-Schrodinger equation, and that's the one that's kind of the more important. And so when it comes to hydrogen atom, by the way, the 3D rigid rotor, which is something I don't really fully understand even today, the 3D rigid rotor wave functions, which I wrote on the board, I wrote a couple of them on the board, you worked with some of them on your homework, those are the right rotational wave functions for the hydrogen atom. So that's why 3D rigid rotor is important. Remember, those wave functions are spherical harmonics. And don't try to remember that other stuff about like 3D particle in a box. Those were called the radial functions. The angular functions for 3D particle in a box were spherical harmonics. The radial part were called Bessel functions. Don't worry about that. I'm not even supposed to bring any of that up. Anyway, so the 3D angular wave functions are the spherical harmonics. You've worked with several of them. 3D rigid rotor. It's going to be the same for the hydrogen atom for reasons I don't fully understand, but anyway. Now, the last bit about spherical harmonics rotation for a particle attached to a string or a hydrogen atom, even though it's not attached to the string, all this stuff still happens, is just to take one last look at, for a particle on a string, it's pure kinetic energy. So this is the energy, it's also the kinetic energy because there's no potential. You know, it's just kind of funky is that for walk through memory lane, right? Free wave, k squared h bar squared over 2m. 2D rigid rotor, m squared h bar squared over 2y. It's always something squared h bar squared divided by whatever. This guy does something different. I wish it was L squared, but it's just not quite. So that's kind of weird. And it just, I don't know, that's just what the math comes out to. And I don't know that there's any special meaning to that, but anyway. Now, you know that it's always momentum squared over 2 times basically mass, or I for when we're doing a rotation moment of inertia. And J can be angular momentum is a vector, and of course it has components. And we can, now again, this should not be blowing your head off. This is r squared is x squared plus y squared plus z squared, right? That's middle school level math. You know that. It's just that these are operators, and they can be complex like this. Sometimes I've had homework assignments where I had you do stuff with this, but your class I just was like whatever. It was kind of like homework 7, where it was just an exercise in bloody awful mathematics. But I just wanted to show you what the operators look like for angular momentum. Yeah, they're a little complicated. Right, not terrible. Okay, and then, and so none of this is all like, you know, this is the important thing, and these are like details. But now let me take those details and come out with something that's actually about as important as the energy itself. I mean, the energy itself is always the thing we're trying to get to, right? But there's this crazy thing happens when you look at the details that ends up being like horribly important, which is, okay, angular momentum, x, y, z. You got momentum, so you see a derivative that's not too surprising, right? It's just a little complicated because these are R cross P, cross products, so you expect that it's going to be a little complicated. What you end up with is an uncertainty principle between z and x and y. Now, nothing's really special about z. We just have to, so what this is saying is that the angular momentum is decomposed into x, y, and z. Again, that's middle school level understanding. But what this uncertainty principle does is says one of the directions is special because you know what it is, but the other 2 are not. Now, again, just because we have to pick something, we just said it's z. Why not? Up seems special to us humans. It doesn't matter to a molecule, but so we're going to say z is the special one. We know what z is, but as soon as we specify what the z component is, we don't know what x and y are. and we don't know absolutely what they are. Remember, if you have absolute certainty in one with an uncertainty principle, then you do not know the others at all. Right now, when we did particle in a box, there's some nuances. You can kind of know where the position is, you can kind of know where the momentum is. This is absolute. You absolutely know what the z component is, so you absolutely do not know the x and y. Now, this is probably all like, what the heck is all this angular momentum? This is sometimes quantum and your physics mechanics, sometimes they actually mesh pretty well. So you actually know this. Angular momentum is this, right? I was doing this last time. And where's J? As I'm drawing this, where's my J? Where's my angular momentum vector? Huh? Is it here? Because this is a plane, not a vector. It's the axis. All right, so when you get confused about all this angular momentum jazz, which I often do because R cross P, I hate that. I hate cross products. I learned cross products, I think, senior or junior year of high school. I hate cross products. But when it comes to rotation, it's not too bad. Just remember, when you get like cross-eyed, it's just the axle. All right, now that's easy. Okay, so I'm drawing, let me match up my picture here. So I'm doing this. And here's the axis, so that's the J. What's the component in Z? Real easy. What's the angle? What's the theta angle? 90 degrees, so what's the Z component? Just project. Like this is Z. Right, this is obviously Z. What's the projection of this vector on my Z axis?
Zero.
Yeah, 0. Yeah, right. See, I mean, look, you did vector stuff. You know vectors. Okay. What's this one? What's the JZ? Oh, of course, everything is freaking H bar. Well, right? What is it? Huh? What's the? Okay, this is the J. This is the angular momentum. So this is going to be the square root of L plus 1 H. Bar. So so I've tilted it, right? So what's the component?
H bar.
H, or let's just say 1, right? Just call it 1. And 2, right? So yeah, again, you know this. Fortunately, sometimes this isn't too terrible. Even rotational quantum mechanics isn't too terrible. Okay, now this is 0. Now don't forget though, the vectors. The vectors are the axles. So if I tilt upward, then I'm basically doing this, right? And then I'm not going to try to do z is equal to 2. Okay, right, mechanics. This was freshman physics. You know this, high school physics. Not too bad. You know this. Okay, now here's where the quantum does something nasty. Okay, I know the component. Let's just do this one again, because this one's easy, right? Right, this is this. All right, now mechanics says that this is exact. Now mechanically, in physics mechanics, what I'm doing right now, you can write a function for it, you know everything. You know exactly what the z component is, you know what the x and y component are. You could write a function in x, y, and z that in time that describe the motion of my cat, I'm flinging my cat around or whatever. And it's all perfect. But quantum says you can't do that. Quantum says that, let's see here. If this is the x component, let's say x is coming out and y is left and right. Okay, what's the x component as I've drawn it? In this case, what's the x component? What's the projection in x? Right, put this vector, give me the x coordinate of this vector. Come on, Jesus, it's easy. 0. The y component is, yeah, square root of the, say it's h bar, right? Okay, you can't do that. You can't do that. You don't know. You just told me the z is 0, the x is 0, the y is that. You just gave me 3 perfect numbers. You can't do that. You can't do that. So here's what quantum does. If you get something spinning, it starts doing this. Now, here's the thing. I know that uncertainty principles, it's like, well, uncertainty principles mean this, that you do this operator stuff and you don't get 0. That's true, but there's a physical, but that has to physically mean something. Remember, I'm always telling you, these equations are things that are real. There's consequences to them, other than just a bunch of squiggly letters, do or not equal a round hole thing, right? So what happens is, if I build a quantity, if I get an electron and I start twirling it around on a string, and I put it in this, and I do it this way, and I let go of it, it starts to turn. It turns on its own. I swear to God, it does this. So again, I shrink myself down, I'm Ant-Man. We're talking about Ant-Man. Anyway, so I'm Ant-Man, and I grab an electron, I put it on a string, and I start whirling it, and I let go. It starts turning on its own. It does that to keep this true. Because when Ant-Man gets this electron and starts turning it, Ant-Man created a system that is fully quantum mechanically defined, which is impossible. So the electron on its own starts taking that angular momentum vector and it starts rotating the angular momentum vector. Okay, so same here and same here. So these pictures are wrong. Let me show you how we do this correctly. And you've probably seen this before. Okay, so I'm going to start with the z of 0. So now remember that when I draw a j vector, that's the axle of the wheel. It's not, the motion is 90 degrees of that, right? Okay, so what happens is you don't really know where it's pointing. So that j, the axle, is rotating like this. Okay, now for the projection on z, those guys, let's do the j of 1. It looks like that. And then maybe it's a little bit wider. I don't know that I'm drawing the absolute length correctly. Okay, so this is like h of 1 and then h of 2. Looks kind of like that. I have to think about what order I draw these in, obviously. Okay. There we go. All right, so there you go. Now, the j vector is right here. This is the j vector, the net j vector. And here's the net j vector. And, of course, here's the z-axis. And here's 2h. And the 1h is inside the cones. But hopefully you follow. I hope you're following here that, again, it's easy to draw the 0, 1. That's this, but I draw a circle because I'm saying that the axle is actually rotating in the xy plane. And then if there's a component in the z direction, and there's a component in the z direction, the reason that I'm drawing this, why am I drawing anything with 0, 1, or 2 projections? Because those are the solutions to the Schrodinger equation for rotation. So do what I just did like this, except angle it, right? So the rotor is 90 degrees, remember that's the axle. Okay, now let's say that I just drew, now one thing is I'm not drawing the minus components. Remember, if there is a 0, 1, and 2 z component positive, then there has to be one negative, right? So I'm only drawing part of it just because this is the limit of what I can draw. Now, if I put this on the test, I should be able to ask you a question. You should be able to answer me right now with what you know. What kind of orbital is this? And that would mean SP, we're talking rotation. That means SPDF. Let's just say that we're going to stop there. Which one is it? SPD or F? Now note that I didn't draw the negative ones. To help you out, how many different rotational states are there? I've drawn 3. How many are there total? 5. What kind of orbital am I talking about? SPDF? D. Right. This has to be, if I've drawn all the positive ones, this has to be an L of 2. L of 0 is S. L of 1 is P. And L of 2 is D. And that means the M sub L, of course, are -2, -1. Again, I didn't draw that just because I can't draw all that much. And then you know that there's 5D orbitals. 5D orbitals. You know that, right? So again, if all of this is a bit overwhelming, J vectors are the axle of the wheel. You know SPDF, you know that quite well. You know that there's one S orbital, you know that there's three P's, you know that there's 5 Ds. You got that worked out, and this is just what it looks like in this weird way to represent this uncertainty principle. So, okay, now this ends up being hideously important to NMR, but before I get to NMR and the hydrogen atom, which we will cover next, I gotta now tell you something about, this is like actually the subject of my PhD thesis, which was inconclusive. You're gonna love this, spin. Okay, spin is a form of angular momentum. Now I understand a electron tied to a string being was around. I understand an H2 tumbling, pirouetting, tumbling. All of that is totally sensible. I can look at a cheerleader, take the baton and spin it. All of this totally makes sense. This is also angular momentum. Sorry, not really. It's not angular momentum, it acts like. Okay, so spin is a property of subatomic particles that acts as angular momentum, but we don't think it is angular momentum. In fact, we don't know what it is because we can't figure it out, and we've actually figured out there is no way to figure it out, which is hideous, right? Now, I can do all kinds of spectroscopy to know that if I have an H2, I can know that it's tumbling. I can use light to do that. But when it comes to subatomic particles, you tell me, what do I use to do spectroscopy on a subatomic particle? No answers? If you could, you'd win a Nobel Prize. No one has any ability to do spectroscopy on subatomic particles. We don't know what these things look like. We can't shrink Ant-Man can, I know, but we can't shrink ourselves down and actually look at these things, and we don't know what's happening. It's basically like an electron. An electron is a sphere. We think of these things as spherical, and it's spinning. Wow, that came out so shockingly well. I'm going to post that on Imgur or something. Anyway, it is as though an electron has an axis and is rotating on it. But we're pretty sure that's not true. The spin, instead of a J operator, it's going to be an S operator. And if it acts on a spin wave function, it returns the following. Square root of S times S plus 1. So of course S squared is would be like the energy, but anyway, so the angular momentum is just like L, where the result is square root of L times L plus 1 H bar. Spin is S times S plus 1. S tends to be 0, half, 1, 1.5. Okay. Now that's all fine, but here's the thing. It gets even a little funkier here. You can think of my taking an electron and spinning it in such a way as I'm going to make it be a d electron, or I won't spin it at all, and it's an s electron. This is not negotiable. Particles take a certain angular momentum and they keep it. You can't change it. It's an intrinsic property. So this is why we think that what I just drew, this is not true. If something was rotating, I should be able to like make it rotate faster, or it might do it on its own, or slower, or something. These SOBs only rotate, if that's what it is, which we don't think it is, we don't know. It always does it with the same umph, and it never changes, which is weird, right? Now let me go over some other weird things. So lots of things are spin half. Now again, remember, I can't use light to make a spin thing go higher. It's always a half. Examples are, what am I doing? Electrons. electrons. And now here's the thing. I'm going to write down their masses, and I'll explain why this is important in a second. Of course, I'm in kilograms. It's minus 31, by the way. You've probably had enough calculator questions to know that. Okay, so electrons are spin 1/2. And that means that they also have M sub s, which is like the Z component, M sub s. So that's minus 1/2. So they have degeneracies. Okay, now other things that are spin 1/2 include protons and neutrons. Neutrons are kind of the same as protons. They have almost exactly the same mass. There's like a thousandth of a percent difference. So I'm just going to write protons, but that's the same thing for neutrons. And those are like way, way, way heavier. And yet they also are spin 1/2. Now here's one, this is a big reason why we don't think that these are the electron, or that instead of electron now it's a proton or a neutron. How could something that's basically 2,000 times heavier, how can it have the same spin when it has very different masses? Remember that angular momentum is R cross P. P is related to mass. P is momentum, mv. How can these have the exact same rotational characteristics? I mean, one of them is 2,000 times heavier. We could also go down lower. Quarks, which comprise protons, are 4 times 10 to the, oh, sorry, those are in between, right? Quarks make protons. 3 quarks make a proton. Something like that. And up, down, charmed, whatever, blue. I don't know what really quarks are, but I know they're spin 1/2, they make protons. They have spin too. All right, so what about this?
Can you describe spin and what spin of 1/2 is compared to spin of 1?
Okay, so yeah, that's oddly about to do that. So now I just want to point out that, okay, so spin means that things comprised of things with spin, which is everything, like atoms, right? So let's take a hydrogen atom. It has a proton and an electron. That means its angular momentum depends on how fast the electron's whizzing around. That's what we've been covering. That's in your physics mechanics class. That's not too hard, aside from the fact that there's quantized levels, aside from this drawing right here. That's where it gets a little bit fuzzy. But still, though, it's all quite sensible. The electron is spinning around the hydrogen, around the proton, and that's a form of angular momentum, which again, that's relatively understandable. But if you want to describe the total angular momentum of this object, this hydrogen atom, you have to include the spin angular momentum of the electron and the proton. So you actually have 3 angular momentums. Now, have you ever seen on YouTube, I've tried to find videos of this, I know they exist, but I had trouble, I was actually looking for one the other day. Imagine that you get a gyroscope. I mean, you had these as a kid, right? Gyroscope. You're right, you had one. It's like heavy metal axle, right? And then you have a little string and you turn it, and then you can put it on a little holder, right? And it would like rotate. It would rotate this way. I mean, you know what I'm talking about, right?
Yes.
Okay, now imagine that, and you can do this if you're really freaking careful. Imagine you get a smaller gyroscope and you put it at the tip of that one. And maybe it's perfectly standing up, in which case it doesn't do anything. Maybe you could tilt it. It's totally going to mess with the bottom one. Anyway, the point of this is that an electron is like this. This big guy is like the way it rotates around the nucleus, but this little guy sitting on top of it is like its own angular momentum. Now, it's unfortunately sitting on not a little cone, again, like you had when you were a little kid. It's actually sitting on another gyroscope, which is the proton. Look, this gets pretty hideously complicated. I'm just describing a hydrogen atom. My point being is that all these spins add up. There's the spin rotation, which again is incredibly simple, but everything else has some other type of spin that is not it rotating, but behaves exactly as though it is rotating. And we don't know what it is, we have no way of figuring it out, but when we treat it like when we treat these like a bunch of freaking gyroscopes, we get exactly the right answer. In terms of like spectroscopy, we're getting to that in like 2 weeks. So that's how to think of this. It's another type of spin action, although it's not really spinning. And we're not going to get into this so much in this class, but I can tell you the reason that it becomes kind of complicated is if you need to describe the entire angular momentum of an object, you have to treat all of these angular momentums like vectors, and you have to add them up like vectors. Not terrible, but complicated enough you can't ignore it either. And so when we're describing the net angular momentum of a hydrogen atom, it's not whether it's an sp or d orbital, that's 1/3 of it. I also need to take into account the angular momentum of the nucleus and the spin component of the electron inherent to just being an electron. Now the reason that's important is that if this thing absorbs light, it has to absorb that thing's angular momentum. You see why it's kind of complicated? Because this is like, it's like an electronic circuit. The whole thing matters. So if this is going to absorb light and absorb its angular momentum, the way that angular momentum gets partitioned can get complicated. So anyway, and it's so complicated that you actually need to go to grad school and get a PhD to actually understand how to do that properly. I'm just pointing out that, you know, like a coupled set of gyroscopes, it gets complicated. And they all affect each other. Yeah. Now you asked about M sub, what about other spins, right? Because I mentioned that these don't change. I've got a spin, what have I done? I wrote an M sub, an S sub 0. S sub 0, I've got a couple, let's see, what have we got an example here? Okay, that is a Higgs boson. That is the Higgs boson. So, here's the thing I want to point out. Well, here, let me give you one other example. S sub 1 is a gluon. Gluon. What's a gluon? You don't know? Jesus, what the hell? Who are you people? That's the strong nuclear force. Gluons are responsible for the strong nuclear force. And let me see, I got another one. Oh, I got another S of 1. Light. Light has spin of 1. Remember, I told you it has angular momentum. Remember your homework part? Does it have M sub S values? What would they be? What's the subquantum numbers? It's just like this, right? That guy has imagine I was talking about the type of angular momentum that was spin. Same picture applies. If something had a spin of 2, and I don't know of any examples of spin 2 of subatomic particles, but it would have 3 sublevels. What about light with a spin of 1 h bar, of course? Do you have any? 3, minus 1, 0, and 1. But now here's this crazy factoid you've never heard of. There's no 0 S sub L, S sub something. Oh, I've already forgotten. Anyway, M sub S. M sub S. There's no M sub S of 0. Do you know why?
Because light needs angular momentum.
Because of what?
Light needs angular momentum.
No, well, I know. I'm telling you it has angular momentum. But no. You can have... no, hold on. What you're saying that this isn't rotating. That's rotating. It's just the projection is in the z-axis. It has no projection in the z-axis. That's kind of meaningless, really. Now, here's the answer. Think back to homework number 3 when I asked you this exact same question, which I am now very likely going to do on the final. Do any of you remember the answer now? Right, because this is circularly polarized light. That's right, circularly polarized light. I know it's kind of counterintuitive. The minus 1 is right, the positive 1 is left. And the 0, if it happened, would be in the direction of propagation, but you run into a weird constant speed of light. Remember that? That was on your 3rd homework? Okay, I'd hope so. Okay, now, I was going to tell you a little bit more. Okay, now you may notice that there's some differences here. You notice how all of these have mass? What are the mass of these guys? None. They don't have mass. So nature does some weird stuff. half spin, half integer spin, mostly 1/2. Those are subatomic particles that give the universe mass. But mass by itself is useless. Mass needs force. Forces come in integer spin subatomic particles. Light moves the universe around quite a bit, right? Higgs boson, gravity, strong nuclear force, holds things, holds the nuclei together. We're all kind of screwed if we don't have our nuclei held together. So these are your forces that hold matter together. And that's now PhD in subatomic physics. Actually, you're on your way. So, what do you think? So I'm not going to probably bring this up. I might bring that up again, anyway. I'm not going to bring this up again, but I've actually always been interested in subatomic physics because of what I just said. I just think that's kind of cool. And you can find YouTube videos that describe this a little bit more, and they're usually meant for like folks at our level. So, so you can follow them. What do you think? Is that,
So if you're getting matter from energy, does that mean the Higgs boson, gluon, and light can turn into protons, electrons, and quarks?
There is a thought that, okay, so when you learn quantum mechanics at a graduate level, and I had a full year at Berkeley, and I learned in the physics department, you learn that you really learn some wacky stuff. And part of me thinks that that's because people really don't know all the answers yet. One of the things that you learn is that matter appears from nowhere, but very briefly. There's this concept that if something happens to an absurdly fast extent, it's unobservable, but it did happen. And we're talking like sub-femtosecond. Okay, so what can happen is people believe that sometimes matter, like, okay, here's empty space. Sometimes like an electron, an electron and an electron and a positron appear simultaneously in outer space. And they appear and they disappear. So that's kind of what you're describing. They do it so quickly that it's so quick, it's not even measurable. I don't mean practically, I mean it's done so quickly like I could never measure this with any experiment because I run into some, remember my crazy long story about diffraction gratings? How diffraction gratings don't really have photons destroying each other because that would mess up the constant energy of the universe. It doesn't happen that way. I cannot measure this event occurring because I would be breaking nature's laws. But it does happen according to theory. Okay.
If you can't measure it, then how do you know it's actually happening?
Because all the equations say it's happening. Which is kind of BS-y, right? Yeah. That's what I think. Okay, but who's ever heard of Hawking radiation? Right? So, yeah, Hawking radiation. This is how you can detect black holes. This is why black holes are shedding energy. Okay, here's how it works. An electron and a positron simultaneously pop up somewhere in the universe. Here's the event horizon. Here's the event horizon of a black hole. The electron gets sucked in, the positron escapes. I don't know that it's electrons and positrons, it may be photons anyway, something like that. That is what Hawking radiation is. That's how black holes can cease to exist. Because this is actually a way of shedding energy. So apparently that is something that has been experimentally verified that black holes do this. So this would be proof that this is true, that matter actually does appear out of nowhere, it just disappears real quick, and you know it because of when it accidentally happens on the rim of a black hole. God, that sounds so cool, doesn't it? Jesus, isn't that neat? Don't you want to watch YouTube videos on this stuff? I swear to God, there are YouTube videos that totally explain this stuff, and it's really fascinating. So I would recommend watching it, it's just that that's not really quite what this class is about. Anyway, so I can move on. Yeah, I really can't be spending more time on this because we have to get to the hydrogen atom. Now I have to mention spin angular momentum because of this. Now, maybe don't write this down, you know this. We're going to get into this a little bit later in spectroscopy. I was talking about d orbitals. Now, you guys are engineers, do you have to take inorganic? Ooh. Now, but you know this. You know that with the right kind of metal compound, the orbitals will split. You've heard of this before, right? Now, you know that when you start adding electrons, you do it this way, right? Yeah, right. Now you see, this is where spin matters. Spin is causing you to add electrons in this way, and then you do it this way, and then you go up here and you do it that way. Now, the reason that this is important is this is magnetic. This is like really magnetic. This is less magnetic, and that's non-magnetic. So that's why this matters. So it's the Aufbau principle. Remember that, the Aufbau, the build-up principle. It's how you fill electrons into orbitals, because and that's spin, right? This is the S-type. So when you drew little arrows on electrons, you were drawing their angular momentum as being up or down. The fact that there's an arrow is S of 1/2, and the up or down is the M sub S, is plus or minus also 1/2. Right, so that's where that comes from. And you learned back as freshmen, maybe even high school, how to do the Aufbau principle, and it's all because the angular momentum is forcing you to do that. And I'll tell you a little bit more about why that is. Now, I know that you're used to doing the Aufbau principle again in high school, but why you can't have, why not do this? Why not do this? Why not? Any ideas? It's a fundamental force of nature. This is like the speed of light. To do this would be the same thing as traveling faster or slow. To do this would be the same thing as traveling faster than the speed of light. You can't do this. You can't have two objects that are spin 1/2 in the same orbital. You can do it with spin 1 objects, but not spin 1/2 objects. Because, and again, that, you're thinking, why is that? I don't know. Why is the speed of light 3 × 10⁸ meters per second? I don't know, but I know it's constant. Why can't I do this? I don't know. It's one of the rules of nature. Now, because of that, you have to only pair spin up and spin down. Because of that, you do the Aufbau principle. You do the build up just the way I drew it, just the way you learned in high school and freshman. Right? Because of that, you can't have two of these in the same spot. So that's why that's important. Okay. So now let me introduce hydrogen atom in the 5 minutes I have left, which I was supposed to spend the entire lecture on. I do find this stuff kind of fascinating, though. And it makes you look smart, right? Now you can tell your family about Hawking radiation and all that. So, H atom. And I just put on YouTube when I go to sleep at night, and cats making my face anyway. Okay, so H atom. So I'm going to just go over some things, some little factoids about the hydrogen atom, and we'll start on, I'm going to do this the way I've done everything. I'll write up the Hamiltonian, which, as I mentioned at the beginning of the class, is hideous. And then I'll write wave functions, and then we'll apply the wave functions to the Hamiltonian. There's like weird factoids, like turning points. I'll go over those, and then we're done with quantum. So we're actually I think this is the end of quantum this week. Wait, what is today? Is it Wednesday or Monday?
Wednesday.
All right, Wednesday, so it's Friday. So we'll go on for an hour then. I have no idea. So I guess we have till next Wednesday. And then we're done with quantum, and then we're going to just cover like spectroscopy and kinetics, and then that's it. Anyway, okay, so we're back in the 1930s. All of this, everything you've learned in this class was learned from like 1930 to 1935 almost exclusively. 1900, people start getting electricity. The first thing chemists did was build vacuum chambers, right? It was like just the go-to thing. When they had vacuum chambers, they would then leak gas into them. They would put hydrogen. Then, because everything was, they would then put really high discharge plates, and they would literally shoot lightning inside of the vacuum chamber with a little hydrogen in it. They also made hydrogen by electrolysis, and they would see that there was a glow. The emission wavelengths were determined by some constant. So there was discrete colors of light This stuff looks kind of bluish, by the way. If you've ever seen this done, it's not hard to imagine, right? If you have like an arc discharge inside of a dilute gas chamber, you imagine it's kind of blue for hydrogen. Now, if it's like red or whatnot, that's how neon signs work, right? If you have phosphors in the same thing, that's where that comes from. But hydrogen is kind of a bluish glow, so the constant's kind of high, and it works like this. It comes in these lines that they figured out very quickly. Follow this rule, where N1 and 2 are whole numbers, and N2 is equal to N1 plus 1. Okay, so again, you build a vacuum chamber, leak hydrogen into it, not that hard as long as you have some electricity. It's actually shockingly easy. They had gratings, we talked about diffraction gratings, they had detectors, they can get spectra, and they see these very specific emission lines. And there's a pattern to it, they quickly figure out this is the pattern. That if this is 1, this is 2, and then 1 over 4 squared minus 1 times this constant is where you see a line. And then you can actually make, every combination for like probably 10 or 20. You basically take N1 and make it go from 1 to 10, and you can reasonably observe all that. So that's how they knew that the pattern is pretty clear, that this is correct. Now, if this was freshman chemistry, what I would be doing is telling you, oh, this is, you probably had this in freshman chemistry, this is what they observed from hydrogen atom, and then you learn that energy states are quantized, and yada, 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 and what fluorescence is. But now that for this class, guess what this is? N, I'm using N for a specific reason. You had it in freshman in high school. What kind of number gives you, emission is energy, what kind of numbers dictate energy? It was on the test in 2 different places. Quantum number, right, I heard somebody say it's a quantum number. Quantum number, right? This is excited state minus the ground state. So you can see that we're going to solve the hydrogen. So I'm going to write the Schrodinger equation. I'm going to write wave functions. I'm going to get energies. There's a quantum number that tells you which one you're dealing with, which wave function you're dealing with. N of 1 is a ground state, N of 2, yada, 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 are higher states. When things fluoresce, it's because you've got an excited state. See that? Ground state plus 1 is excited state, pretty sensible, right? And so this tells you the energy minus the energy of the ground state gives you the emission. So this is obviously a quantum number. And it goes from 1, 2, 3. Does this sound familiar to you at all? Can you guess what this is? Here's a big hint. I'm going to draw an object. You tell me if you recognize it. Huh? Look familiar? What is that? It's a robotic mouse. It's got, no, I'm just kidding. Yes, it's the periodic table. All right, it's the periodic table. N equals 1. N equals 2. These are the rows of the periodic table. That's where Mendeleev came up with this stuff. Not that he didn't actually know this. He just figured it out from observation like here. These are the quantum numbers. Now, which wave function do you think solves them? Right? You know that we're going to get this. We get a radial, we get an angular, 1 second, we get we've got a theta and a phi. There's a certain m, there's a certain l. What am I missing? N. Right. Right, so it works like this. Now we've done enough angle stuff, you should be okay. I can have a d orbital, and then m tells me which one of them they are. It's like dz squared or x squared minus y squared. But this one tells you what row you're on in the periodic table. Guess which one gives you the energy? That one, right. So what we're going to do, when we write down the Hamiltonian, we're going to start out with the angles. This one gets knocked off. This one gets knocked off. We're left with the radial. Guess where the energy is? The radial. And then we're done, then you graduate. All right, okay, folks, I'll be sending emails if you have a little trouble on the